So we're starting today with a little bit of factoring practice. This is just a warm-up problem to help us remember this process for factoring a quadratic like this. And one thing that's happened as we've been factoring these quadratics is a few of you have started saying, well, I've been doing it like this, which is a little bit different, but I'm getting the right answers. Is that okay? The answer is yes, as long as it works first time, every time. And now we're going to find out how that's going, because this one, with certain methods, this one could give you trouble. Because I know some people have gotten into this habit of saying, oh, well, the way we get 6 is we multiply 3 times 2. But that's not going to be the case with this one. So let's work through using the method that we've done together. We call that the grouping method. Remember, with that, we start by multiplying a times c. In this case, 6 times 4. That tells me what I'm going to multiply to. And so I'm going to multiply to 24, because that's 6 times 4. And I'm going to add to the middle number. That is the b value. And so that means I need to add to 25. So what two numbers multiply to 24 and add to 25? Yep, it's got to be 1 times 24 there. So that's then the combination I'm going to be using here. So I now split my 25 up into 1 and 24. So then it's going to become 6x squared plus 1x plus 24x plus the 4. And yes, you don't have to write it as 1x here. You certainly can, and in fact I'd even encourage you, go ahead and write that just as x. All right, now remember why we do that. We do that so that we then can factor just the first 2 terms, and then factor just the last 2 terms. So I'm just going to factor those individually now. And so when I factor those first 2 terms, 6x squared plus x, notice the only thing that factors out of that is just an x. There's no numbers that I can divide out of both of those terms. And so then that's going to leave me with 6x plus 1 inside of the parentheses there. Then we do plus. Now I'm looking at the last 2. And so what can I divide both of those by? 4. So I factor a 4 out of both of those. And so we're going to go 4 parentheses 6x plus 1. And notice the 6x plus 1, that is the stuff that's inside the parentheses, is the same for both of them. And that's a good sign. If it's not the same, then you know we ran into an error somewhere along the line. All right, one last step. I'm now going to factor that 6x plus 1 out of both terms. When I do that, notice I'm left with an x and a plus 4 behind. And so my other set of parentheses is going to be x plus 4. And that is done. That is it. That's your correct answer. Yes, if you gave your answer as x plus 4 times 6x plus 1, that is the same thing. And so you can change the order of the parentheses, just not changing the stuff inside of the parentheses. A little side note now. I talked about how some of you might get thrown off by this one depending on your method. You notice that this one did not end up being 2 times 3 to get the 6, and it did not end up being 2 times 2 to get the 4. We actually had to go through this method to find what combination it was, because there's lots of different ways we can get some of these different numbers. Mostly we've just been working with nice, pretty numbers up to this point, ones where really the only way to get 6 has been 2 and 3. But as we go on, you're going to find us working with more and more numbers that have more combinations than just the one way to get it. And so get used to using this kind of a method, or if that method that you've been using still worked great for this, then you're still in good shape. All right, so today, this is the sort of equation that we're going to be dealing with. Something where we have a number multiplied out front of our x squared. Now, we've seen this sort of thing before. In the past, we graphed something like y equals 2 times the absolute value of x. And we saw what that did. Remember there, it gave us a v shape still, but it was a steeper v. We basically talked about it having like a slope of 2. Same kind of thing's going to happen, but the word slope cannot be used today, because slope only works if something is straight. And our graph today, because we're going to be graphing x squared, you know it's going to be that u-shaped graph. It's not straight. And so slope is no longer going to be something we can talk about. Let's actually see what does happen with this thing. So I'm going to start by bringing us back to the table. You don't have to write this down. But this was the table we made when we first graphed the parent function, y equals just x squared. And we found that like we had the point 2, 4 there because if I square 2, I get 4. If I square 3, I get 9, and so on. And that's why we have that pattern of plot the first point and then go over 3 up 9, over 4 up 16, etc. Well, we can take that same kind of an idea and use it for the 2x squared. Because notice for 2x squared, I'm taking my x squared values, that is all of these, and I'm multiplying them by the 2. And so I'm just going to multiply each of these numbers by 2. When I do that, these are the new values we get. So notice that basically what has happened is that my old y value has now been multiplied by 2. That is, when I go and plot these points, since the y value has been doubled, that means I have to go up twice as far with every point that I plot. So let's actually see that taking place here and start plotting some points for this equation. So notice 0, 0 didn't change because 0 times 2 is still 0. So we still start there. The only thing that ever changes your vertex point here is a plus or a minus. Only adding or subtracting will change that. Multiplying does not. All right, from there, we normally would go over 1 and up 1. But notice in this case we're not. I need to go up twice as far, so I'm going to go over 1 and up 2. And you notice, yes, we do that on both sides. We do it for the positive and for the negative 1 for the x. All right, next up, I normally would go over 2 and up 4. I'm not going to do that though, notice. Instead of over 2 up 4, I'm going to go over 2 and up 8. That is, I'm going up twice as far as I normally would. And notice how I keep describing it there? That's the way that you end up doing this as you plot these points without having to make a whole table. Is to say, okay, normally I go up 4, but in this case, I'm doubling it. So I go up 8. And so we can use that same kind of thought process to see where that next point would go, because I would say, well, normally I go over 3 and up 9. Instead, for this one, because I'm multiplying by 2, I would have to go over 3 and up 18. Well, that one definitely does not fit on my graphing grid, though. So we go ahead and we draw our curve through those points. And yes, notice it is still a curve. It's still a U-shaped graph. When it starts getting steep like this, it can be tempting to try to make it look like a straight V there in the middle, but it's not. We still should have that curve leveling out right at the vertex. So this is the way your graph should end up looking. And now we got to talk about what that transformation that we just applied actually is, because we aren't going to describe the transformation as a multiplication by 2. Notice we were going up twice as far. So it's like I took the point that used to be up 1 and I pulled it upwards. The point that used to be up 4, I pulled it upwards. Like I'm taking this bar that's drawn across the graph at that point and I'm pulling that bar up. It has the effect of taking that whole graph and just stretching it upwards, which is why we then call this a vertical stretch. And then we get specific by saying by a factor of 2. And so add this also to your graph. Make note of it kind of on your grid or next to it so that you can keep track of that. That multiplying by 2 is a vertical stretch by a factor of 2. So having seen that last example, that means you now can deal with something that looks as complicated as this. All right, so when we go to start making this graph then, we start by doing the shifting. And the shifting works the same way as it always has. The 3 doesn't change anything of that. So like this minus 4 that we have inside the parentheses. Does that move it up, down, left, or right? It's in with x, therefore it moves it along the x-axis. Minus goes to the right. And remember, that's how I can know that. And so if you ever get stuck, that's how you can remember. If it's in with x, it moves along the x-axis. All right, the minus 8, it's hanging on the end. Well, that means it's got to go up and down. Minus, yep, it does go down. And so I put my first point right 4, down 8. That is, I have my vertex form equation given here, and I put my point at 4, negative 8. Notice that the 3 did not change that. What the 3 does change is where we go from there. So Normally, I go over 1 and up 1. In this case, though, the 3 changes that. Remember that the 3 is a vertical stretch. It doesn't change how far I go over, only how far I go up. So I'm still going to go over 1, but instead of going up 1, I'm going to go up 3. Because 1 times 3 is 3. Next up, I normally, and notice how every time I'm going to plot a point with this, I'm saying, what do I normally do? Normally, I go over 2 and up 4 next, because 2 squared is 4. Okay, so I have that in mind, and then I say, multiply it by 3. Only how far I go up, though. So I normally go up 4. 4 times 3 is 12. So that's telling me that for this point, I'm going to go over 2 and up 12. And so I count up 12. Remember, I'm counting up from the vertex. All right, from there, normally it's over 3 and up 9. In this case, it would be over 3 and up how far?
27.
27, exactly, because we'd have to do 3 times that 9. Well, I can't exactly do that, can I? That's off my graphing grid at least. Maybe you set up yours a little bit bigger, but that's all I can fit on mine. So at that point, I would go ahead and draw the curve that goes through those points. Again, make sure that you're keeping it curvy right around the vertex. That is, flatten out around that vertex. Now, with stretches, we're multiplying by something. These problems inevitably come along, so we're going to deal with them right now. We're multiplying still by a number, but the number is now a fraction. And so we need to see what that does. The nice part is, it basically follows the same rules as what we did before. So notice in this equation, there's no shift. So that means my first point is still going to be at 0, 0. Nothing changed there. And then we say, well, what do I normally do? I normally go over 1, up 1. In this case, I'm multiplying by a half. That means I'm still going over 1, but I'm going up how far? I'm going up half of the normal 1. So I'm going to go up only a half. Yes, we are going to be plotting our points at some non-integer values here. All right, so let's see what happens with the next one then. Normally, I'd go over 2, up 4. Instead of going over 2, up 4, I'm going to go over 2 and up half as far. What's half of 4? 2. So that means I'm going to go over 2 and up 2. Still over the same amount. All right, next up, we normally go over 3 and up 9. In this case, I'm going to have to go up half as far. What's half of 9? 4.5, exactly. So I'm going to go over 3 and up 4.5. So you notice we're just taking whatever I normally do and going up only half as far. Okay, we can keep going with that. Normally we don't get a plot the over 4 points, but in this case we will. Over 4 is going to be up normally how far? 16. So in this case, it'd be half of 16, which is 8. So I go over 4 and up 8. What about if we go over 5? When we go over 5, how far up should we normally go? 5 squared is 25. So it would be 25, yeah. What's half of 25? 12.5. That's off my graphing grid. So that means I've plotted all the points that'll fit, so I can go ahead and draw the curve that goes through those points. Now, having done that, I again want to describe what this transformation is. Now, you notice in this case, I normally had a point at 1, 1, but it kind of got squished down. And then I normally have a point at 2, 4, and that got squished down. And then the point at 3, 9, that got squished down. It's kind of like, again, I had this bar across my graph, and somebody just squished it down and like put a weight on my graph and compressed the whole thing down. You notice stretch wouldn't make much sense here, because when we stretch something, it gets bigger. So even though we're making it the same kind of basic idea, we do change the word in the transformation. We call this a vertical compression by a factor of 1/2. So again, add that to your graph that you made, or right next to it, whatever, so you can remember that's what that's called. All right, so when we go and start making this graph, again, you'll notice that there's no shifts involved, so your first point's still at 0, 0. And then our first point that we plot, it's normally over 1, up 1. So in this case, it's over 1 and up a third. And then normally our next point is over 2 and up 4. So I'm still going to go over 2, but I'm going to go up 1/3 times 4. That is 1/3 of 4, or you could actually calculate it by doing 4 divided by 3. Notice 4 divided by 3 is a fraction, 4/3. If you're pretty good with your fractions, which I hope you are, you're going to see that that is the same thing as 1 and 1/3. So I go up to 1, and then I go up 1/3 more. Okay, then from there, I'm going to go over 3, and normally it's up 9. Well, what's 1/3 of 9? 3. So instead of over 3 up 9, it's going to be over 3 up 3. Okay. We're definitely going to be able to fit more points on, aren't we? Let's keep going. Over 4. That's normally up 16. So I'm going to have to do 16 divided by 3. Which again, do a little quick conversion there into a mixed number. That's 5 1/3. So I'm going to go over 4 and up 5 and 1/3. Next up, over 5. 5 squared is 25, so it's going to be 25/3. Okay, 25/3, that's 8 1/3. Now, if you're one that has a little bit of trouble doing those quick conversions on the fractions, you can always plug it into your calculator and do 25 divided by 3, and it would tell you 8.3 repeating. So then you'd be able to plot that way, should you get stuck otherwise. Okay, let's go over 6 next. We haven't ever actually been able to get out to 6 before. When I go over 6, how far up do I normally go?
36.
36, because 6 squared is 36. So what is 36 divided by 3? 12. Well, I can just barely fit that on my graphing grid. You might not have been able to if you went up to 10. That'd be okay. But if you can fit it, plot it. And then that's definitely going to be the last one I can fit. So we go ahead and we draw the graph that goes through that. Now, I'm going to go off on a little bit of a tangent here for a moment. When we did absolute value, remember we talked about that number out front being like slope. Some people still really try to have that mean the same thing here. But notice that if you took that the same way that you did when you were dealing with absolute value, a slope of 1/3 would mean that from your starting point, you go up 1 and over 3. Notice that's way off from where we actually want the point to be. And so it's been a vertical compression or a vertical stretch all along. It's just that when it's straight, we can turn it into this bigger fraction and with the rise over run thing. But that only works if it's straight.